Just kidding. Okay, let's talk about the lab now. We'll continue talking about static equilibrium on Monday, but let's go to our lab. So what's the idea of the lab here? No other questions? Okay, let me adjust this. Okay, here's the idea of the lab. We want to measure the moment of inertia of our iOLab as it is rotated about the y-axis, right? If you think about it, moment of inertia of an object could be three different numbers, right? It could be a moment of inertia rotated about this axis, rotated about this axis, or rotated about this axis, which is my third one, this axis, right? So the moment of inertia of an object is really, in a sense, a set of three numbers, okay? And if you really want to get fancy, what if I rotated it about some axis that was a combination of several other axes? Well, then the moment of inertia would be some combination of the moments of inertia about the three principal axes. And in fact, the actual moment of inertia of an object is a matrix, a 3x3 matrix that represents the moment of inertia about the three normal principal axes, okay, which you can then multiply by the axis you have chosen to rotate something around to get the moment of inertia about that axis. And that 3x3 matrix is something called a tensor. So when I say what is the moment of inertia of this in the real physics world, it's a 3x3 tensor that describes all the moments of inertia about any possible axis you could spin this around. So that's your first indication of a tensor. The tensor of inertia, it's called. Okay, but we're just going to pretend that, we're not going to pretend, we're actually only going to rotate this thing around the y-axis, right? The axis in the y direction. So we only care about the moment of inertia of this thing through the y-axis, okay? And what is the theoretical moment of inertia of an object rotated about this axis? Well, you can look it up in your book. Here, let's share it. Let me share it here. There it is. Look at that. The moment of inertia of a slab rotated about its center is 1/12 m times the square, the sum of the squares of the two dimensions that are perpendicular to the axis of rotation. So in the case of our iOLab, the theoretical moment of inertia is 1/12 mass of the iOLab times the square of the thickness of the iOLab plus the square of the width of the iOLab. Two numbers you can easily measure, right? Make sure you're measuring the correct dimensions. It's not the long axis that determines the moment of inertia. It's the thickness and the width. Okay, that's the theoretical value of the moment of inertia. How are we going to calculate the experimental value? You're going to take, I don't know why I can't see my demonstration screen. It keeps disappearing. Okay, there we go. So you're going to take your iOLab. You're going to get 2 tape rolls. Most tape rolls you buy in the store have a standard inside diameter. I think it's like 4.5 inches. And the designer of the iOLab very cleverly made the iOLab just the right size so it'll just perfectly fit inside a roll of tape. Okay, so you're going to have to go to the 99-cent store or Walgreens and buy yourself 2 rolls of tape. Their thickness doesn't matter. You can get, in this case, I got the cheapo one that's just a few rolls of duct tape. You can get a giant one that's, 10,000 miles of duct tape. Doesn't matter. And as long as the inside is the standard 4.5 inches that fits on the iOLab. The iOlab sits inside these tape rolls. We're going to put it on a inclined plane and let it roll. Okay. And what is that going to tell us? Well, when we put two tape rolls, let's go back to this. Okay, that's better. So when we put two tape rolls on our iOLab, we create a new object that has a new moment of inertia. The moment of inertia of this tape roll plus iOLab combo is the moment of inertia of two rolls of tape plus the moment of inertia of the iOLab. Okay? The moment of inertia of a roll of tape, well, you can calculate that if you know, oh, where is it? Am I not sharing the moments of inertia? Do you guys see the moments of inertia page?
Yes, we do.
Yeah, okay. So the moment of inertia of a tape roll is the moment of inertia of a annular cylinder. 1/2 the mass of a roll of tape times the sum of the squares of the inner radius and the outer radius, both of which you can easily measure. Okay, so the moment of inertia of the tape roll plus iOLab combo should be the moment of inertia of two rolls of tape plus the moment of inertia of the iOLab. Okay, so let's go back to sharing the prediction sheet now. So we're going to apply conservation of energy to this contraption of an iOLab stuck between two rolls of tape. Okay, so conservation of energy means that the iOLab tape roll combo, if we put it on our inclined plane, is going to roll down a height h, okay, and as you know, trade its potential energy for its kinetic energy. In other words, mgh, the initial potential energy of that rolling object, is equal to the final kinetic energy. And the final kinetic energy is the sum of the translational plus rotational kinetic energy of that iOLab combo. Okay, so now, if we go back to the prediction sheet, let's zoom in a little so I can write on here. Okay, so we have mgh is 1/2 mv squared plus 1/2 I omega squared, right? But since this object, when it gets to the bottom of the inclined plane, is rolling, then it must be true that V is omega R. But what R? Let's think about this carefully. What R is that R in V equals omega R? Here's my, oops, let me go back to the demo. Here's my iOLab tape roll combo. These tape rolls are a little loose, but here it is, and I let it roll down. What is the R in that V equals omega R equation I just wrote? Anybody? Think about what's going on here. What is the R? Physically, what does it represent in this case? Very good. You're almost. It's the outer radius, not the outer diameter, right? But it's the radius of the outside of your tape roll, right? Because that is the radius of your entire object. So it is the outside radius of the tape roll. Make sure you see why that is, okay? outside radius of tape roll. Okay, so now we can just solve for I. So what is that? Let's see. But unfortunately, H, we don't know H, right? Because all we measure is the length that the iOLab rolls and the angle theta. But that's not too bad, right? Because sine theta is H over L, and therefore H is L sine theta. Right? Okay, so we can make this mg L sine theta is 1/2 mv squared plus 1/2 I omega squared. Oh, but that's 1/2 m omega squared over r squared plus 1/2 I omega squared, right? And that's 1/2 m over r squared plus 1/2 I times omega squared, right? No, I'm going to isolate I, don't I? Sorry. So that's, what is that? That's, I guess I got to start multiplying the other side. So then I have 2 mgl sine theta equals m omega squared over r squared plus I omega squared. So 2 mgl sine theta minus m omega squared over r squared times 1 over omega squared equals I. Okay, and that's just a rewritten version of this. Okay. I hope everyone got through that little bit of algebra there. So all we have to do is measure M, the mass of the combination of the tape rolls plus the iOLab. Measure L, the length of the path it rolls down the slope. Theta, the angle of inclination of the slope. R, the outer radius of the tape roll. And finally, maybe most importantly, omega. Right? Omega, the final angular speed of the tape roll when it gets to the bottom. And that is where the iOLab comes in. So let's show you. Okay, you guys see my iOLab software? Yes, good. Okay, so I'm going to turn on my iOLab. Make sure it's connecting. It wasn't connecting earlier. Okay, I'm going to bring up a graph of gyroscope. Remember, gyroscope is measuring the angular velocities at the point G in the center of the iOLab. But it can measure the angular velocity about any of the three axes, X, Y, and Z, which is the only omega we care about. When this thing rolls down, what is the only omega we really care to measure? About which axis? Anybody? X, Y, or Z? Which is the only axis that we care about? What is the axis about which this iOLab is rotating?
X.
X is this axis, isn't it?
Yeah, my bad.
It's not rotating on that axis. Which axis? Z? Z is this axis. It's not rotating on this axis. Best 1 out of 3. It's rotating about the y-axis, right? It's rotating this way. That's rotating about the long axis of the iOLab. So the only omega we care about is omega y. So you can unclick omega x and omega z, start recording, let the iOLab roll. And lo and behold, what do you see? Whoa, stop. Look at that. Beautiful. Now, I chose to let my iOLab roll this way, which resulted in a negative omega. I could have turned it around and rolled this way and gotten a positive omega. It doesn't really matter. But I can just go down here to below my graph and choose reverse y-axis. And there is my beautiful graph of omega as a function of time. And like all our labs, you got to really think about what this is depicting. What is this kind of showing you? Let me zoom into the fillet of our data here. What is this physically showing you is going on? What is that graph showing you? Anybody? We have here omega in radians per second as a function of time. And it was 0, 0, 0, and then it started increasing linearly, and then poof, it went back down to 0. What does that physically mean is going on with my iOLab? You really got to understand this in order to do this lab. Anybody? Remember, omega is the rate at which this thing is rotating, the angular speed. So what is this physically showing is going on?
The thing is speeding up.
Okay, speeding up is maybe not quite the right term, but speeding up angularly.
Yeah.
In other words, it's starting to rotate faster and faster and faster, which makes perfect sense because it's rolling downhill, right? And right here, somewhere around here is where it fell off my track. So the final angular velocity, when it got to the bottom of my ramp here, looks like it was about 22.12 radians per second. That is omega. That is the final angular speed that has been created by the fact that my contraption lost potential energy and gained kinetic energy. So that is the crucial piece of data that you are going to measure with the iOLab. 22.17 radians per second. Now yours is, of course, going to be different because you'll have a different angle and a different length, all of which you'll measure. But in my case, I got about 22.2 radians per second. And by measuring theta and measuring the mass of the tapes and the mass of the iOLab and the inner and outer radii of the tapes, I can then find the moment of inertia of the contraption. I can subtract the moments of inertia of the two tape rolls. And finally, I will be left with just a moment of inertia of the iOLab itself, which I can compare to what the theory says it should be. Okay? This is probably the most involved lab we're going to do, but I'm hoping it makes sense. Now, of course, as in all labs, think carefully about sources of error. Anyone see any sources of error off the top of their head? Remember, sources of error are random things over which you have no control that are going to affect the accuracy of your result. Anyone see just a few? There's tons of them, but anyone see one off the top of their head? Hint, hint, hint. Look at the iOLab and look at the theoretical. Oh, cool. Doesn't move with it. All right. There's the theoretical expression for the moment of inertia of our iOLab. Anyone see any sources of error? Nothing? What does this theoretical, is anybody out there? Am I the only one here? No, okay, good. There's 9 people there, or 10. What does this theoretical calculation for the moment of inertia assume about our object? Look at the picture. Look at the iOLab. Are they the same thing? You guys are killing me. Okay, you know what? I'm not even going to answer that. I'm going to let you think about it. The answer is no, they are not the same thing. There are some big differences between the iOLab and that slab shown in the picture. I'll let you think about what they are. Okay, several steps involved here. Any questions about what you're going to do? You're going to have to go get yourself a pair of tape rolls. These were 97 cents each at a store whose name I will not mention, okay? Remember, you can get your rolls any size you want as long as the inner diameter is such that the iOLab slips in and fits nicely. Take your iOLab to the store to make sure that it fits, okay? You're going to have to measure the masses, the 2 radii of your tape rolls. You're going to have to measure, of course, the mass of the iOLab, which you should be very used to doing by now. You're going to have to measure the dimensions of the iOLab in the correct 2 of the 3-dimensional directions. You're going to have to measure the angle of inclination of your slope, and you're going to have to measure the length of the slope that the iOLab rolls down. And from all those measurements, you should be able to come up with the experimental value for the moment of inertia of the iOLab. And you will compare that to the theoretical value of that iOLab. Okay? What do you guys think? This one is a little bit involved. There's a fair number of measurements you're going to have to make here. Make sure you do them correctly. Make sure you have the right units, right? Measure radii in meters. Measure mass in kilograms. Okay? Measure length in meters. Okay? Make sure you're measuring the length correctly. You're measuring the length from the bottom to the point where you release it. Okay? Any questions? This is a fun one. This is a fun one. We'll see what kind of results you get. Okay? Think, as usual, about sources of error as you go along. There's 1,000,001 sources of error in this experiment. Think about the tape rolls. Think about the iOLab. Think about the assumptions you are making about the tape rolls and the iOLab. What assumptions are you making about them and their properties? There's a bunch of them. Think carefully. Human error is not a source of error. Okay? This is making some sense, I hope. Dead silence out there. Somebody has to say, yes, it makes sense, or no, I have no idea what you're talking about.
It makes sense.
Thank you, Aiden. Awesome. I appreciate it. Okay. All right. Go work on some homework problems. We just kind of dipped our toe into static equilibrium, but there's really not much else to do except a few sample problems. So we will finish doing a few more sample problems of static equilibrium. And then by Wednesday, we will start on the last of our 3 miscellaneous chapters, gravitation, the first actual real force we will be studying, and the only real force we'll be studying this semester. And then we have to zip through fluids and simple harmonic motion so we can have enough time to do a little review before the final. Okay.